Hello and welcome to Time to Revise with Crazy Physics 2020. I'm sure our episodes have been a blessing to you. This afternoon we're going to continue with our vertical projectile motion as we prepare for our Friday exam, and we will be looking at work, energy and power. I know a lot of you are anticipating what this episode holds for you. Trust me, you're gonna love this. Alright, now when we look at work, energy and power, oh by the way, please do not forget, send us a feedback, and here are all the details that you need. Name, school, province, feedback, and you have our email address there. We would love to read from you. For those of you that have sent us feedbacks, thank you so much for the positive feedbacks and the things we can do better. We really appreciate that. Alright, now let's look at work, energy and power. I'm just going to summarize quickly and then we'll look at a question. Work, energy and power. Alright, first we know that work is a scalar quantity, right? Work is a scalar quantity. And the formula for work is F delta X cos theta, where F is a force. And when we talk about a force, we could talk about two types of forces, which are conservative and non-conservative forces. And on the non-conservative, we like to use the acronym FAT: friction, applied force, and tension. And on the conservative, we talk about the force of gravity. Another force that is falls under conservative will be your electrostatic force, just for knowledge purposes there. All right. So your F there is going to be one of these forces, either conservative or non-conservative. And don't forget that the unit of this is newtons. And then we talk about displacement, which is always measured in meters. Now the question is this theta. What is theta? Theta is the angle between a particular force and the displacement. But one thing I can quickly just tell you is this, that the theta for frictional force will always be equal to 180 degrees, and so we can take our clue from that. Theta for friction will always be 180 degrees. That's going to help you a lot if you keep your eyes on that. All right, so we have conservative and non-conservative, and we have our angle theta and delta x. By the way, work can be measured in joules. All right, let's change this quickly. What is the unit? No, not a calculator. We need this. All right, now work, remember we said it is F delta x cos theta. The unit of this is joules. Now joules is equivalent to, what is the unit of force? Newton. And what is the unit of my displacement? Meters. So 1 joule is equal to 1 Newton meter. You could find this in your multiple choice. Which of the following is equivalent to 1 joules of energy? So that is that. All right. Now quickly, because it's a crash course, it is important to know your energy principles. And basically, when we talk about energy principles, we talk about your work energy theorem. And this, guys, is on the formula page, written as W net equals to delta EK. And if we transcribe this into words, what does this mean? Let's get something brighter. Let's get something brighter. The net work done. So this is the net work done on an object. Now, equals, right, which means is equal to the what? The change delta in, what is EK? Kinetic energy of the object. And this is what you get most of the time in your question 5.2 or 5.3, where the examiner says, state your work energy theorem in words. Work energy. So just use your formula page to transcribe that into English in words, and you are basically done. All right. So the net work done is equal to the change in kinetic energy of an object. And when it comes to calculation, you need to understand that when you say W net, it means all forces working on the object. Sum of all forces. Now let me say sum of, let's claim this, sum of the net work done, because it network, rather sum of the work done. Sum of work done by all what? Forces. Is that okay? YWNC, this you would find on your formula page as change in kinetic and change in potential. This is the work, sum of the work done. Now, this is sum of work done by non-conservative what? Forces. Very key. What are my non-conservative forces again? We said fat, friction, applied, and tension. Now, very key point that I'm going to write here. In an isolated system, crazy physics, we would say it's a fat-free. It's fat-free. You know, fat-free milk. This is a fat-free system. It means we do not have any of these forces. Basically, we are saying there is no friction, there is no tension, or let me keep that arrangement. There is no applied force, and there is no tension. It means these guys are not present. Therefore, the work done by non-conservative in an isolated system will be therefore equal to 0. Just to quickly look at something, and then we'll look at a question here. Now, if that is equal to 0, let's write the formula again. The work done by non-conservative is equal to EK plus what? Change in EP. Now, so in an isolated system, just going to put that here. It means that this is 0, and this becomes half m VF squared final change. We subtract. All right, I hope that still makes sense. Plus what? MGH final minus MGH what? Initial. If I decide to move all the initials to one side, what do I have? MGI squared plus MGH initial, and that will be equal to, so I move all the initials to one side, and I have all the finals to one side. What would you notice here? Oh, this is EK initial plus EP initial. This is EK final plus what? EP final. And what is this? This is the definition of mechanical energy. The sum of the sum of kinetic plus potential. So basically we are saying E mech initial is equal to E mech what? Final. And this is known as the law of conservation of mechanical energy. The law of conservation of mechanical what? Energy. So this is a crash course. Now, it is important for you to understand this. So, in an isolated system, the total mechanical energy is conserved. All right, so in an isolated system, the total mechanical energy is conserved, and that is the law of conservation of mechanical energy. Do not forget, it is in an isolated system. Is that fine? All right. Now, I'm going to say something very important here, that normal force and FG perpendicular will do no work on an object because they are perpendicular to the displacement. I love this note. Perpendicular to the displacement. And when we say perpendicular, what do we mean? It means theta equals to 90 degrees. So if I tell you work done by normal force, it will be normal force delta x cos theta. And if my theta is 90, then I know that I'm going to have normal force delta x cos 90, and that will be equal to 0. So the same thing with work done by FG perpendicular. Please take note, not FG, but FG perpendicular. So they do no work because they are perpendicular to the displacement. Very important point. Okay, time is running again. Now, there are situations where, listen, where you do not have, okay, when you are not given VF and VI. We're just going to do a quick manipulation here. Understand that, okay, your work, we said work is F delta x cos theta, right? Now, I want us to see something here. My work net is change in kinetic energy. That means my work net is equal to half m Vf squared minus Vi squared. But check what I wrote here. When you are not given Vf and Vi, and I'm supposed to use this, I can then introduce my equations of motion. Look at this equation of motion. All right, Vf squared equals to Vi squared plus 2a delta x. Let's move this over here. What are we going to have? Vf squared minus Vi squared equals to 2a. Oh, awesome. So that means I can then replace this. I hope it makes sense by now saying my W net equals to half m. Instead of writing Vf squared minus Vi squared, I can then write 2a delta x. Ah, I see something coming up here. This is half. Oh, the half and the 2 can actually divide each other. All right, and I have ma delta x. But hold on, what is ma? Ma is what? F net. Oh, so it means my work net can be written as F net delta x cos theta, where theta is now equal to 0. So that cos theta will be equal to 1 because the object will accelerate in the direction of the net force. So the angle between them would be 0. All right. I hope this crash course helps you to quickly understand work. And it is very important. Please do not play with your free, you call it free body, I call it free max diagram. Please learn to draw your free body diagram. This is what will guide you. I am going to look at a question right now in 10 minutes or so that we can then get this out of the way. All right, look at this question. All right, 12 minutes. A skateboarder skates from point A. I'm going to quickly get my point A. All right, skates from point A on the track, which is at vertical height of 15 meters. So my height, 15 meters. And aims to come to rest at point D. Oh, aims there to come to rest at D. On the other side as shown, section AB is frictionless. Okay, no friction. By the way, it means there's no tension. And this guy is just sliding. We're told a skateboarder skates. Okay, we're going to check something here. All right. BC and CD are rough. Just going to do something here just for us to know that they are rough. Okay. And the word rough simply tells you there is frictional force. The combined mass of the skateboarder and the skateboard is 55. Let's put that information down. M equals to 55 kg. The skateboarder experiences a frictional force of 15 newtons while moving from point C to D. Fk equals to 15 newtons. All right. Ignore the effect of air friction. All right. 5.1. Do you notice we stated that a while ago? And because of time, I am just going to consider that then. That in an isolated system, the total mechanical energy is conserved. All right. 5.2. Calculate the kinetic energy of the skateboarder at point B. Wait, we're looking for kinetic energy at point B. But what do I know? Point A to B is a fat-free system, which means that EMEC is conserved. And when EMEC is conserved, it simply means that the EMEC at point A equals to the EMEC at point B. Now, what is EMEC? It is EK plus EP all at point A. I want to do this so that I just don't want to jump into telling you that mechanical energy is equal to potential energy. All right, and I'm going to go to the next page and expand that formula. Can run. All right, so half mv squared plus mgh all at point A is equal to half mv squared plus mgh all at point B. All right, at point A, the object is at rest. The object starts from the maximum height there. All right, so this is m, and then that's 0. But m here is 55 times 9,8, and the height is 15. Let's go back quickly to see the height, 15. All right, and then what do I have here? Half 55 v squared plus mg. My height is 0. Why is my height 0? The object is right on the ground there. So let's quickly use our calculators to get the answer. So basically this is 0 and that is 0. Let me just circle it so that it doesn't waste my time. Oh, beautiful. So it means we can actually work this out. Just going to grab a calculator and work out everything on the calculator with you. So I'm going to have 55 times 9,8 g, and the height is 15. That gives me that. Now, if I cross multiply, the 2 goes up there. Is that fine? And then I'm going to divide both sides by 55. But that is v squared. I need to get the square root of v squared, and that will give me 17,16. So v is 17,16 meters per. Oh no, guys, we are actually looking, we shouldn't have done this. We are looking for kinetic energy. Sorry, I was looking for velocity. This is kinetic energy. So this is EK. Oh, so my EK, I remember, is 294 joules. You don't need to get the velocity to go back. You are wasting time. All right, quickly. State the work energy theorem in words. That is also done. We stated that a while ago, if you remember. What did we say? We said that what? Let me just quickly show you again. The net work done on an object is equal to the change in kinetic energy of the object. Beautiful. That is very straightforward, and that is done. Look at the question. Use energy principles to calculate the kinetic energy of the skateboarder at point C. What do you notice about point B and C? It is a straight line, but there is friction involved, which is what? 15. Okay, so I'm just going to get you a page, or let's work here. I have very few minutes. So here is my point B, and there is my point C, and the kinetic energy here is 294 joules. But there is friction, so let's try to draw a free body diagram. The object is on a surface, so we have normal, and then we have what? Force of gravity. That's my normal force. Now, the only force acting here would be friction, which opposes the direction of motion. So since it is friction, I can just say my work net is equal to change in kinetic energy. And the only force that is doing work, remember, no work here, no work here, will be friction. So can I then come here and say frictional force multiplied by delta x cos theta, because the only one doing work is friction. And here we're going to talk about half mvf squared minus half mvi squared. What are we looking for again? Don't lose sight. Kinetic energy at point C, which is, this is going to be my initial, and this is going to be my final. So basically what I am looking for is that. Now we're given friction as 15. What is delta x? 10 meters. I told you earlier on that if it's friction, it's always cos what? 180. Now this is EK at point C. Is that fine? That's my final. All right. Minus, what's the kinetic energy here? 294. Can I throw the 294 over? What will be my answer? All right, so it is 15 times 10 cos 180. All right, close the bracket. Now if I bring that over there, it becomes positive, plus 294, and that will give me 144 joules. So EKC is 144 joules of energy. Awesome. Let's quickly get through the last question. I hope it's making sense. Simplified. Oh no, we're not going here. Time will not allow us to go here. Now calculate the magnitude of the frictional force along BC that will enable the skateboarder to come to rest. So we're looking at that point. I'm going to quickly extract this diagram for us. All right. Okay, I'm just going to extract that diagram. It's giving me some grief, but not a problem. We know what the question is, and we're going to do that. So this is what we have. We have a surface there, but mind you, don't forget it is rough. CD, VF equals to 0. We do have our value there. What's the value? 15 degrees and 10 meters. Lovely. Let's write everything we know. 15 degrees and 10 meters. What do we know here? We know the kinetic energy as 144 joules. What are we looking for, guys? We are looking for the value of the frictional force. Listen, draw your free body diagram. Very easy for you. Okay, let's just make sure we draw our free body diagram. That's going to be my normal, and this is going to be my FG perpendicular. Now my FG parallel, always acting down and parallel, and then I have this needs to be completely straight. Should have used straight lines, and I have what? Friction. Please make sure that you try as much as possible to make sure that these lines are parallel. Okay, let's just quickly get this correct. Those lines, try as much as possible that they are parallel. Beautiful. Frictional force. Okay, now if I use my work net or work done by non-conservative, time will not allow me. I was going to show you the two differences. Work done by non-conservative, or let's use work net here. Work net equals to what? Change in kinetic what? Energy. I'm talking about work net, so the sum of the two forces. Work done by FG parallel plus work done by what? Friction equals to half mvf squared minus half mvi squared. All right, I'm cloning this page or just going to the next page. Don't forget what this is. This is mg sine. I use alpha. You'd see why I use alpha. All right, so I know that I have, let me just quickly write this, plus work done by what? Friction again equals to final velocity, final kinetic minus what? Initial kinetic. Now, what will this be? This is Fg parallel, my original formula for work, all right, plus frictional force delta x cos theta, and that should equal to this whole concept there. Just going to copy and paste it. There we go. Just trying to save time. All right, good. Now, this here is mg sine alpha delta x cos theta. I do not know my friction, so I'm going to have it like that. Guys, if you learn to simplify your work, it's going to be very easy for you. Simplify. Okay. I should have just written that. I would be done. All right, just a few more seconds and I will be done. Now, what is the mass? The mass is 55. What is G? 9,8 sine 15. My delta X is 10. Cos, I quickly want to explain this. I told you earlier on that friction is always 180 when it comes to the angle. Now, since FG parallel is on the same side with friction, it automatically attributes that angle to itself as well. So if they are on the same side, it becomes 180. If it was on the other side, then it will be a 0. That just quickly helps you there. All right. Plus, I do not know my friction. 10 cos what? 180 will therefore be equal to half. Do I know my final kinetic energy? Yes, because that will be 0. We want to get to a point where it stops. Minus 144. All right, the initial kinetic energy. Look, everything is done already for you here. All we need to do is to just get an answer, which is 0.45 newtons. That is your work energy and power simplified.